Hey, this is Dr. Williamson going over the basics, real basics of atomic absorption and going over Beer's law. If I have a container that has a molecule in it that appears to be colored, say this blue color, the reason why it's blue colored is it absorbs some wavelengths of light and does not absorb other wavelengths of light. And the net result is my eyes see a blue color as a result. The way that this incoming light coming in is absorbed by the molecule in there is that the incoming light comes in as photons, and these photons get absorbed by electrons at a low energy level in a atomic orbital, or we could talk about molecular orbitals later. And the energy from this photon is absorbed to bump the electron up to a specific higher energy level. And that photon of light is then absorbed and never makes it out the other side of my container. Okay, so we would say that photon of light is absorbed. We would say the light is absorbed. Exactly how much light is absorbed is determined by measuring the intensity of the incoming light. We call that I naught. And the intensity of the outgoing light. And I have this exactly backwards, like a dummy. That should be equals minus log I over I naught. That's what I get for typing wrong, but I'm not going to restart this whole video all over again. So let's pretend you never saw that. Okay. And so this will always be a ratio of ratio smaller than 1. The ratio I to I naught will always be a ratio smaller than 1 and smaller. That's how we would measure the absorption. And how much light is absorbed depends on how well that molecule absorbs photons. Some molecules absorb photons better than others. It also depends on how long this path is. If I have a container that's twice as big, this light beam is going to run into twice as many molecules. So I'm going to get twice as much absorption. Kind of makes sense. So it depends on this path length. So when we do our experiments, we're going to choose a container that has a consistent path length or consistent diameter. And we're going to use these things called cuvettes, which have a path length of 1 centimeter. And then it also depends on how concentrated it is, because the more molecules we have in there, the more crowded it is, the more molecules the light beam is going to run into, and the more absorption we will have, which leads us to what's called Beer's law. Beer's law says that the absorption is proportional to the concentration of the molecule that's in there. And if we use the same molecule every time for our experiments, then letter A will be constant because it's unique for that molecule. And if we use the same size container every time, we would be able to measure the concentration measure the concentration, the absorption of our molecule as a function of its concentration. And we would get a line that looked like something like this. We're at zero concentration. We should have zero absorbance, because with no molecule in there, we should have no absorbance. And the slope of this line, and that's poorly written, but that'll be y2 minus y1 over x2 minus x1 will be equal to little a times little b. Don't use rise over run. But anyway, if we do that, we'll be able to predict later, if we measure an unknown sample and get its absorption, we'll then be able to tell what the concentration is for an unknown sample once we make our Beer's law plot. Okay, that's the fundamentals of Beer's law. I apologize for getting that messed up. It's a human mistake. But anyway, I hope that explains the fundamentals of that. I'll try and make a better video on this later. But anyway, that's good enough for now. Okay, then I'll talk to you guys later.